Okay, so so this research is a joint work with these wonderful guys. So the one is Taiji Suzuki, he's in the Kyushu Institute of Technology, and another guy is Daniel, he's from the University of Toronto. And these are my students, Katsusato Oko and Naoki Nishikawa. Okay, so basically, as I said, so I will talk about the optimization of the mean field neural networks. But this optimization problem is non-convex. So because the optimization of a neural network is highly non-convex, so it's a difficult problem. And moreover, so basically we consider a kind of an over-parameterized network. That means we consider a very wide neural network. So therefore, we have a large number of parameters. So that is, we needed to optimize very high-dimensional optimization problem. And it is also non-convex. It is non-convex and high-dimensional. Also, how to solve that? That is a problem. So to solve that problem, so we consider the mean field rangeband dynamics. Okay. So then I gave some convergence analysis, and interestingly, so we have a global optimal convergence guarantee. So we have some theoretical guarantee of the global optimality. Okay. And we finally, I will propose some finite particle and discrete time algorithm. So basically, the mean field rangeband dynamics is defined in a probability measure space. And we needed to approximate that probability measure by a finite sample. And also, this is defined in the continuous time dynamics. So we need to consider a kind of a discretization of time. So we do the both of them, okay? Discretization of the probability measure and time discretization. And we give some methods that have a theoretical guarantee of global convergence, and moreover, it has the convergence rate is like a polynomial time. So yeah, it's nice. Okay. So, so as I said, the optimization of a neural network is highly non-convex. So basically, we want to minimize the loss functions. Okay, then by minimizing the loss functions, so we want to find some neural network that explains the data very well. Okay, but the problem is that the parameter size could be very large. Like for example, in a real neural network, it can the size of the parameters can be like billions of dimensions. It is very high dimensional, and interestingly, even though the landscape is highly non-convex, the practical usage of stochastic gradient descent is very successful. So why is it? So maybe just using the gradient descent, maybe the solution can be stacked in the local optimal solution. But using a stochastic gradient descent, in practice, we usually find near global optimal solutions. So because we find a very low training error, and we see very low test errors. So that means we are finding near global optimal solutions. So why is it? To explain that, so we consider a kind of a noisy gradient descent. So it is a little bit difficult to analyze the stochastic gradient descent itself. But instead of that, we consider a kind of mathematically idealized dynamics. That is a noisy gradient descent. Okay. So yeah, that is what I will consider in this presentation. Okay. So anyway, so to explain why SGD works well, so the one reason is that if you consider a kind of an over-parameterized network, so then every local optimal is connected to the global optimal. So that means that there is no spurious local optimal. So let us consider two-layer neural network. So then if the width of the two-layer neural network is larger than the sample size, so then there is no spurious local optimal. So this kind of local optimal does not appear. So the landscape looks like this. So because of this theorem, so we expect that by running a gradient descent, maybe finally, so we can find a global optimal solution. Okay. So the intuition is like this. So if you have a very wide network, then that wide network has a good representation power. So it can represent many functions. So therefore, we can find a good descent directions because this model can realize large size of functions in some function class like L2 space. So then this model can find a good descent direction. Okay, so yeah, the intuition can be illustrated by this figure like this. Okay, to justify this kind of intuition, so there are two types of analysis. So one is a neural tangential kernel technique, and another one is a mean field analysis. Okay, in a neural tangential kernel analysis, so roughly speaking, if you consider a very wide neural network, and if you initialize the parameter in a specific way, so if you consider some specific scaling of the parameters, then the Taylor expansion along the initial solution gives a good approximation of the neural network. So that means that the neural network can be approximated by a linear model. So that means that in other words, neural network can be well approximated by some specific kernel model. So that is called a neural tangential kernel. Okay. But in this analysis, so the kernel function, so the feature extraction function is fixed. So we cannot analyze any feature extraction ability of a neural network. So yeah, so this means that so the neural network is approximate. So in this regime, so we can approximate a neural network by some kernel model in which the kernel function is fixed with which is defined by some initial solutions. Okay. So instead of a neural tangential kernel, so we consider the so-called mean field analysis. This is the today's target. Yeah. Yeah, basically so. Yeah, basically so. So this is a yeah. Okay, so let me consider. Okay, it depends on the situation. It depends on the scaling. For some specific scaling, like a neural tangential kernel scaling, so then it is shown that there is but with some initializations, we can find the global optimal solution. So yeah, the statement is it's a little bit different from this one, but we can show the gradient descent can find a global optimal solution. But okay, yeah, it depends on the starting point. But I'm not sure. Direct extension. There is I don't know. I don't know some result that corresponds to the direct extension of this to the deep network. So yeah. Yeah, I think it is shown only in a two-layer neural network. Yeah.
Tells us that this local optimas get reduced in this wide network.
So sorry, so could you say this?
Is there theoretical proof that can back the statement that in a wide network, this local optimas they tend to reduce a lot?
Use?
Like these spurious local optimas, they don't happen in wide two-layer neural network.
Oh yeah. So yeah, this is the theorem. Yeah, this is a theorem. Yeah, so this is rigorously shown. Yeah, you're right. But the problem, the important point is, even though there is no spurious local optimal, it is not obvious that gradient descent can find a global optimal. Maybe so this plateau is very, very large, and so maybe the gradient descent can stack around here. So it is a little bit different from the optimization guarantee. Yeah. So then, therefore, we need some other theories to guarantee the global optimality of the gradient descent, like this analysis. Yeah.
The analysis also consider restart. For example, you could start the different starting.
Yeah, they are. Yeah. So if you even though the neural network is somehow narrow, and some assumptions like a teacher-student structure, if you try many initializations with high probability, like larger than 1/2, so you can find a global.
Depends with the stochasticity of the optimization algorithm. So if I have like full batch gradient descent,
okay. In the neural tangential kernel regime, so full batch gradient is okay. So you don't need a stochasticity here. But for the mean field analysis, you need a stochasticity. So it depends on some situations. So in a neural tangential kernel, so then the model is completely approximated by the linear model. So it is just a linear. So it is kind of very trivial to show the global optimality. Yeah. Okay. Good. Okay, so let's go into the noisy gradient descent. Sorry, there appears some mathematics here, but okay, but I think it's okay. Yeah. So let us consider this noisy gradient descent. Okay, so as I said, we want to optimize this loss function L. Okay, this is basically loss function, which is obtained like this. Okay, to optimize this loss function, to minimize this loss function, so basically we consider this, the noisy gradient descent. This is called gradient arrangement dynamics. So yeah, this is a continuous time dynamics. If you stop here, this is a continuous time gradient descent because this is minus over. Okay. So this is because minus over the gradient over loss function. So this is a steepest descent direction. Okay, so but just using this full batch gradient descent, so it will lead to the local optimal solution. So we add some stochasticity here. So this is so-called gradient arrangement dynamics. So dBT is a Brownian motion. And beta is the so-called inverse temperature parameter. So that controls the strength of the noise. So by adding this noise, so it is expected the solution can head out of the local optimal, then it will reach the global optimal solution. So its time discretization can be given by that case. This is called gradient arrangement dynamics. So because we have discretized the time, so then the dynamics can be written by like this. So maybe you are more familiar to this formula. So the xt is updated to xp plus 1 by this formula. So here eta is the step size. So yeah, if you stop here, so this is just a gradient descent, but we add a Gaussian noise here, and so here appears the step size again. But anyway, so the basic idea is that we update xt by a gradient descent and add some Gaussian noise. So then we add some stochasticity, so that maybe we can get out of local optimal. So the illustration is like this. So we update xt by a gradient descent, but by adding a Gaussian noise, it perturbs like this. Then eventually it can get out of the local optimal. Then it finds the global optimal solution. Okay, so from now, so I will show some rigorous justification of this intuition. Okay, so the important point is that this dynamics has a stationary distribution. As t goes to infinity, the distribution of xt converges to this distribution, pi infinity, which is given by exponential of minus beta Lx. This is the probability density function of the stationary distribution. So therefore, the stationary distribution has the highest probability density function around the optimal solution of L. Okay, so the pi infinity looks like this. Okay, so then thank you. So the pi infinity has a high probability density around the minimum of Lx. So because here is a minus, so if L is very small, so then the probability density is high. And here beta is the inverse temperature appearing here. So if beta is large, so then this probability density is much more sharp, and it will concentrate on the optimal solution or optimal value like around here. So therefore, if you run this dynamics xt and then let t go to infinity, then xt concentrates around the global optimal solution. So then you can find a near global optimal solution. So that is our. Anyway, so loss can be 0. So the important information is the relative value of a loss function. So loss can be 0. Yeah.
Like giving slight nudge to the current event. Avoid the local minima. It is like giving a slight nudge.
Slight nudge.
Slight push.
Yeah. Yes, that's right. Yeah. So, but the slight push is just random. It's just randomly getting. We add just a random noise. So then we randomly explore around the local optimal. Then finally, it can find some some path to escape from the local optimum.
That's some intuition behind how much noise to add.
Yeah, it's a good point. It's just a hyperparameter. Yeah, so there are trade-off. There is no freeness. There is trade-off. So if beta is small, it requires much more time for exploration, but it has a much faster convergence in the local regions. So but if beta is small, so then it can explore more faster, but it cannot converge. So because of the large amount of noise. Yeah. Okay, so it is a kind of very different directions. So basically, the Langevin dynamics is independent about the momentum method, but you can combine the momentum method with the Langevin dynamics. Yeah. Okay. Questions? No. Okay. Thank you. Okay. So yeah. So then so here the next question is, so okay, so we know that the station distribution is like this exponential minus beta Rx. So if t is very, very large, then xt will around the optimal solution. So but the next question is how fast the convergence is. Okay, so we have this exponential convergence. So okay, so I explained that. Okay, now so we assume that, so this is a kind of conceptual condition that if we assume the pi infinity, the target the station distribution satisfies so-called log-Sobolev inequality. Okay. So this is very famous in the probability theory literature. Okay, so the log-Sobolev inequality is a property of the station distribution. So suppose that for any probability distribution nu, which is absolutely continuous with respect to pi infinity, satisfies this inequality, then we say pi infinity satisfies the log-Sobolev inequality. Okay, so this inequality says that in the left-hand side, there is a KL divergence between nu and pi infinity. And in the right-hand side, there is a so-called Fisher divergence. Fisher divergence is another divergence. So it also measures a kind of a distance between the distribution nu and pi infinity. So there are two measures of the divergence, the distance between the two distributions. Okay, here KL divergence is bounded by other divergence, Fisher divergence, but there is some constant like here. So this constant CLS is called a log-Sobolev constant. Anyway, if there is some constant such that for any nu, if this is satisfied, we call pi infinity satisfied log-Sobolev inequality. Yeah, so in the next slide, I will show some sufficient condition in which log-Sobolev inequality is satisfied. But yeah, so roughly speaking, so maybe if you are familiar to the optimization theories, there are so-called PL conditions, Polyakov-Zharsky conditions, that says that the loss landscape loss is upper bounded by the square of the gradient of the loss, or the gradient of loss function. So yeah, the objective value is bounded by a kind of a power of a gradient. So then we call it as a PL condition. So this is something like that. So so the objective function is a KL divergence. The KL divergence is bounded by a kind of the gradient of the KL divergence. So in a probability measure space. So in that sense, this corresponds to the PL condition in the probability measure space. So the infinite dimensional counterpart of the PL condition. Okay, so then under this condition, so we have geometric ergodicity like this. Okay, so geometric ergodicity means that the KL divergence between the pi infinity, the station distribution, and the time t distribution of xt. So mu t is the xt's distribution. Okay, so then this converges to 0 in exponential order. That means the distribution of xt converges to this distribution, the target distribution in exponential order. Yeah, so that's nice. So yeah, so here are some conditions in which the log-Sobolev inequality is satisfied. So the one example is that the loss function L is strongly convex. So then we have a log-Sobolev inequality. So if the target, the loss function is convex, then we have well, fast convergence. Okay. But another important property is like this. So if the loss function is given by like this, so here is something like a regularization term, the L2 regularization plus some loss functions. So you see that this is strongly convex. So if there is no loss here, so just if there is only the regularization term, then it satisfies the log sovereign inequality. But there is some additional term here. So, but if this loss function is bounded like this, if this one is bounded like this, so then the station distribution exponential minus beta Lx also satisfies the log sovereign inequality with this constant. So this is so-called small perturbation lemma. So that means that if L is a strongly convex function plus some bounded function, then it always satisfies log sovereign inequality. So yeah, so in the machine learning literature, we oftenly encounter this kind of objective functions. So yeah, it is easy to ensure the log sovereign inequality. But and there are also another examples, but I skip this. This is so important. Okay, so then this is a kind of this slide is a little bit dense slide, but I explain one to one, one by one. Okay, so so then now, so I want to explain why we would need exponential convergence. Okay, so the Grandis-Rangeman dynamics is given by like this. So here mu t is a distribution of xt. So we can show that the mu t satisfies this partial differential equation. So this is called the Fokker-Planck equation. Fokker-Planck equation. So yeah, the mu t satisfies this partial differential equation. So this is coming from the stochastic analysis. And here is the Laplacian of mu t. Laplacian of mu t. So Laplacian of mu t can be decomposed into nabla times nabla log mu t because nabla log mu t is nabla mu t divided by mu t. So nabla mu t divided by mu t, so mu t is cancelled out here. So yeah, this Laplacian can be decomposed into like this. And here is mu t, so mu t is coming here, so nabla L is coming here. So this partial differential equation can be rewritten like this. So if you let here this term as minus vt, so then this partial differential equation can be rewritten by like this. This is so-called continuity equation. Continuity equation. Yeah, this is a very famous and popular in the field of partial differential equation. Okay, so anyway, so we have this continuity equation. So yeah, this kind of a formulation will appear in the next slide. So then we can show that this PDE, this Fokker-Planck equation, tries to minimize this objective function. So in terms of the Wasserstein gradient flow, so it tries to optimize this objective function with respect to the probability measure mu. Okay, so this the objective function is given by the expectation of L with respect to the distribution mu plus some entropy regularization term, entropy term. Okay, so now we are optimizing xt, but xt has a distribution, and then so from high level, so what we are doing can be reinterpreted as an optimization problem in the space of a probability measure. So yeah, there are some another interpretation like this. Okay, so then L is, so we write this objective function as a capital L. Okay, fractal L. So then so we can easily show that the optimal solution of L is given by exponential minus beta Lx. So this is the station distribution. Okay. So this is a kind of a dual formulation of probability distribution. So the Gibbs measure. So anyway, so we have a station distribution like this as a minimizer of L. Okay. So yeah. So for finite t, we have this inequality, but this is okay. So I will say, okay. So finite. No, I'm saying just a finite. Yeah. So the difficulty is that next we need to take the infinity with this. So then there appears a difficulty. So that is the next step. Great. Thank you. Yeah. Okay. So And so here appears another objective function. So how it is related to this Fokker-Planck equation. So here is some reason. Okay. So through some simple calculations, we can see that beta times L is equivalent, almost equivalent to the KL divergence between mu and the station distributed mu star. So this is just a simple calculation. There appears some constant function, but constant can be neglected. Okay, so basically, what we have shown in the previous slide. So L is basically KL divergence. Now, so we take the time derivative of KL divergence with the KL divergence like this. So here we substitute mu t to mu in this formula, and we take time derivative like this. So then, so if mu t is obeying this continuity equation, so minus nabla dot vt mu t, then this can be written by like this. So minus the inner product between vt and this function. Yes. Okay, so what is interesting here is that in our settings, in the grand transform dynamics settings, vt was like this. So vt was given by like this. Okay, so sorry, I go back to here. So vt was like this. So from this Fokker-Planck equation, vt was defined this term, and this is coming here. So then this time derivative becomes this equation. So the time derivative of KL divergence between mu t and mu star is given by minus 1/beta times this quadratic function, this quadratic term. So this is always positive, or always non-negative. And so then, because of the definition of the Fisher divergence, so this term is equivalent to the Fisher divergence between mu t and mu star. Okay, so the time derivative of KL divergence is equivalent to minus 1/beta times Fisher divergence. Now, so we have assumed that the mu star, that the distinction distribution satisfies the log Sobolev inequality. The Fisher divergence is lower bounded by the KL divergence times some constant. So therefore, this can be upper bounded by this term. So here, the time derivative of the KL divergence is bounded by minus some constant, positive constant time KL divergence. Therefore, we have an exponential convergence of the KL divergence. Yeah, so that's good. So, and this is a continuous time dynamics. So there are also many results on the discrete time dynamics. Okay, so for example, from Benparado and Vivisono, so they show the discretized version, time discretized version of the gradient arrangement dynamics has this convergence rate. So we basically have an exponential convergence, but there is some error which is induced by time discretization. Here, eta is the step size. So the step size times some constant factor appears here. So if the step size goes to 0, so then this term goes to 0. Yeah. And so, but this is a convergence in terms of the distribution. So we are also interested in the optimization guarantee. So here is a result about optimization guarantee. So the time t, so at time k, so the solution of xk, the expectation of loss function at xk is the loss function is bounded by this quantity. So basically, these two terms are same as these two terms, and plus so some factor. So this represents some discrepancy between the KL divergence and the loss function value. So there is a d over beta is coming here. So anyway, so even though the objective function L is non-convex, so by assuming some kind of a log Sobolev inequality, we have a global optimal guarantee like this. Okay, yeah. So what I said is the finite dimensional settings. Okay, so next, so we want to extend it to like a infinite or very wide neural network. So that is a mean field arrangement dynamics. So, but the difficulty here is that you can see that in the rate of convergence, there appears a d. D is the dimension, the dimension of the parameter. But if the dimension of the parameter is very large, like 1 million or something like that, we cannot use this bound. So because this term is too large, so then we need some modification. So that is called mean field arrangement dynamics. Okay, so here is some idea of the mean field arrangement. So as we have seen, the arrangement dynamics is it can be interpreted as optimizing the probability distribution of xt. So instead of xt, so we are also optimizing some distribution of xt. So therefore, if we consider some arrangement dynamics, so we can optimize some distribution. So yeah, we use that structure. Okay. So let us consider two-layer neural networks, which is written by like this. So here, Rj is some real number. So this is the second layer parameter, and the Wj is the first layer parameter, and the sigma is a non-linear activation function, like a sigmoid function, hyperbolic tangent, anyway. So yeah, so now, so we take n to infinity. So we consider, over-parameter settings. So then, if the parameters R and W are distributed from some probability measure nu, so if there is suppose that there is some distribution nu, then from this distribution, so R and W are generated, and then this finite average can converge to this expectation by the law of large numbers. So yeah, this is a kind of a mean field representation of the neural network. Okay. So then the good point here is that, so this is linear to the probability distribution nu. Okay, if you look at the parameter like this, so this is non-linear with respect to parameter R and W. This is a highly non-linear. But if you look at the distribution of the parameters, so maybe, so this is written in a major theoretic notation. But if so you can suppose that this nu has some probability density function. Then so this is linear to the probability density function of nu. Okay, so because this is linear, so then if the loss function is a convex function in terms of the function value, so then the optimization becomes easier. Okay. So now, so our viewpoint, important viewpoint is that instead of optimize the parameter itself, we optimize this distribution nu. Okay. So yeah, so we want to optimize some distribution. Then we fit distribution to data. That is what we want to do. Okay. Okay, so here's a derivation of the mean field arrangement dynamics. Okay, so now the loss function can be written by like, so sorry, it is a little bit messy equations, but the idea is very easy. So this is a loss for the ice observations, and this is the neural network. Here, hx is one neuron, hx is one neuron, and x is the parameter of that neuron. Okay, so we have m neurons. For each neuron has a parameter xtm. Okay, so we take its average. So that is the output of the neural network, two-layer neural network. And we also consider this regularization term, this L2 regularization. Okay, so now we apply the gradient arrangement dynamics to optimize these parameters. So then we have this dynamics. Okay, this is basically the gradient descent plus Gaussian noise. Yeah. Now we take the m to infinity. So yeah, so because there is a scale 1 over m, so we are multiplying m here, but you can neglect here. By taking m to infinity, so then this dynamics will converge to like this. Okay. So here f mu is this one, so the integral representation. So where the mu is the distribution of the parameter. So theta, or so here the xt. So xt is coming here as a theta. Okay. So we are taking the expectation with respect to the parameter of the neurons. So f mu is coming here. So yeah. So now mu is the distribution of xt. So mu is the distribution of xt. So then this dynamics converges to like this. Okay. So okay. So then so this is basically the gradient of the loss function, but the difficulty is that the distribution of xt is coming here. So yeah, so this gradient, this term cannot be determined by just one point xt. So just a location of xt does not determine this gradient, but the distribution of xt is also coming here. So this is a difference from the vanilla gradient rangeman dynamics. So this is so because of this, it is called a distribution dependent stochastic differential equation. The distribution is coming here. Okay. So now, so if you let f mu, so instead of this one, so if you write f mu is like this, so depending on the distribution mu, so if you define the loss function plus regularization term is like this, so then we can show that this is a kind of the differentiation of f with respect to the probability measure mu, which is given like this. Yeah. So this is a differentiation with respect to the probability distribution mu. Okay. So what I said, it can be summarized like this. Okay. So we have a model, so mean field model. Mean field neural network is given by like this. This is an expectation of each neuron with respect to the parameter theta. Then so the mu is a distribution of mu. This mu is a distribution of the parameter theta. It's like this. And for f mu, we have a loss function, and we also have a L2 regularization like this. And we take its derivative with respect to mu. So we have this one. Okay, so this is a derivative in a probability measure space. Then we have this this one. Okay, so this can be seen as a kind of linearization of f at the mu. So this is a kind of local linearization of f. So yeah, then the mean field rangeman dynamics is given by like this. So dxt is given by minus of a nabla of this linearization is coming here. This means that we are trying to optimize the loss function f by using some linearization of f. So we consider a kind of a local linearization of f, linear approximation of f, and we try to minimize this by using a gradient rangeman dynamics. And here, so we again, so mu t is the distribution of x. So here are some correspondence to the gradient rangeman dynamics, the vanilla gradient rangeman dynamics. In the gradient rangeman dynamics, f mu was the expectation of L with respect to mu. So it is a linear it is a linear function with respect to mu. Okay. So then if you take its derivative with respect to mu, so then yeah, so please believe that. So if I take a derivative, so because this is a linear function, so then the integrand coming out. So then its derivative becomes L. So if L is substituted here, then we can recover the gradient rangeman dynamics. So therefore, so the mean field gradient rangeman dynamics is a direct extension from gradient rangeman dynamics, where f is generalized to nonlinear functional with respect to the distribution mu. Okay. So by doing so, we can extend the finite dimensional gradient rangeman dynamics to infinite dimensional gradient rangeman dynamics. Yeah. So yeah, based on this observation, so we can say the mean field rangeman dynamics optimizes this objective functions. So in the gradient rangeman dynamics, f was this integral. Yeah, and so this integral plus the entropy term was KL divergence between the spatial distribution and mu t, but now f is replaced by this nonlinear function. So yeah, so we write this as a capital L. Okay, so then through some cumbersome calculations, so we can show that the time derivative of L mu t, fractal L mu t, is given by minus of the integral of Vt squared, where Vt is this term, so which is coming from the Fokker-Planck equation. Okay, so yeah, so we have a Fokker-Planck equation of mu t like this. This is a partial differential equation that determines the dynamics of mu t. Okay. Okay, thank you. So yeah, so we can again rewrite this Fokker-Planck equation like this: nabla over minus Vt times mu t. So we let this term as a minus bt. So then this Fokker-Planck equation can be also a continuity equation, which is obtained by minus nabla dot vt mu t. So yeah, so then based on this definitions, so the time derivative of L can be written by this one. So I skipped some details. So anyway, so we have a minus of vt square is coming here. The vt is this one. Vt is not this one. So this is a kind of a Fisher divergence between mu t and so-called Gibbs measure p mu t. But I skipped some details. So the p mu t is a kind of a, well, proximal point. So if you know the proximal grand descent, so it's like a the next step of the proximal point, proximal grand descent. So yeah, this is a kind of the proximal gap. Yeah. So anyway, so the mu t, and so there are some Fisher divergence between mu t and p mu t is coming here. So yeah, as long as this term is not zero, so then the target well, object L decreases, continue to decrease. Okay, so based on this observation, so finally, so we can show the exponential convergence also for the mean field Langevin dynamics that is presented in this papers. Okay, so we now so in the Granite Langevin dynamics, we have assumed that the station distribution is satisfies the log sovereign inequality. But instead of that, so we assume another conditions. Okay, so we consider p mu. So this is the proximal. This is called the so-called proximal Gibbs measure, which is defined by like this. So here, so this p mu is defined by the minimizer of this objective function, and so this corresponds to the linearized version of the objective function. Okay, so now we take the time differentiation of f with respect to the distribution mu, and we linearize this term, and then optimize this objective function. So we make f as a linearized. We make f linearized like this, and then we optimize this alternative objective. So then that optimizer can be written by like this. So yeah, through some calculations we can see that. So then so if, for example, f contains some L2 regularization like this, if f has some L2 regularization, so and the loss function is bounded, then we can ensure, sorry, the p mu satisfies the log sovereign inequality. Then under that assumptions, so we have an exponential convergence. Yeah, exponential convergence in terms of the fractal L. Yeah. Okay. Okay, so this is our continuous time dynamics. Okay, so I should finish, so maybe 5 minutes or something like that. Okay, so what I said is a continuous time, and also we needed to have a mu t, the distribution of xt. But in practice, we don't have a distribution mu, and we cannot run the continuous time dynamics. So we need to approximate that dynamics, like in a discrete time and finite particle approximation of the distribution. So then we do that. Okay. Okay, but I skip this one. Yeah, but one difficulty is that if you discretize the distribution by some finite particle, like by using the MCMC, so then you can sample some particle from the distribution. But if you discretize some distributions, then there appears some discretization error. Then the problem is that discretization error could propagate through the time, and maybe that error could accumulate in the exponential order. So that is a difficulty. So we want to control that error. So that is a problem, but we can do that. Yeah. So okay, so this is a reformulation of the problem settings. So the original problem is to minimize these objective functions with respect to the distribution nu on the parameter of each neuron. So remember that. So this is the neural network, two-layer neural network. So we want to we optimize the distribution of the parameters. And so, as I said, the mean field range-bound, what mean field range-bound is doing is to optimize this objective function plus some entropy term. So what the mean field range-bound is doing, this optimizes problem. Yeah, so that is written here. Okay, so yeah, so L is given by like this. So the mean field range-bound is minimizing this L like this. Okay. Okay, so anyway, so so this is a alternative objective function with respect to the distribution. So yeah, like this. So here Q is a density function of the distribution U. So Q is a density function. Well, the important point here is that so this is a convex function with respect to density function Q. So this is a convex. So this is a kind of an infinite dimensional convex optimization problem. Okay? But so that is a good point. But the difficult point is that so here appears an expectation with respect to the density function Q. So the expectation is not so easy. So there is no explicit form of this expectation. So we need to approximate this expectation by using something like an MCMC, like that. So what we do is a kind of a combination of convex optimization and MCMC. Okay, so the basic strategy is that. Okay, so I go back. Basic strategy is that, but we basically optimize this object function by using usual gradient descent or something like that. We perform some optimization technique on the measure space. So you can use the gradient descent or dual averaging method or anything such a method. Okay, but so to compute the gradient, we need this expectation because the loss function is determined by this expectation. So that expectation is approximated by MCMC. So that is a basic strategy. Okay. We combine the gradient descent and MCMC. So this is the illustrations. So suppose that at time t we have a distribution QT. Then the expectation is approximated by some sampling from this distribution QT. This can be done by something like MCMC. By using this particle approximation, we can compute the gradient of QT, and QT is updated to QT plus 1. And then we again sample some particles from this distribution. So we repeat this. Okay, so this is just summary. So I don't explain some details here. But anyway, so we have so far proposed two methods. One is a particle dual averaging method. This is a kind of a combination of MCMC and a dual nested dual averaging method. So by using this one, so we can obtain a polynomial order method, so polynomial order time complexity method. And we can also combine some so-called stochastic dual coordinate ascent technique and such an MCMC method. And we also have an exponential convergence. So yeah, we have proposed two methods. So I briefly explain particle dual averaging method. Then I will finish my presentation. Okay. Okay. So as I said, what we want to do is to optimize this objective function with respect to the distribution Q. Okay. So but this term is nonlinear. So first we approximated this by a linear functional. Like this is very much like a optimization in a finite dimensional space. In a finite dimensional space, we approximate the loss function by a linear function by using gradient, and then so we update we update the parameter by using linearization. So what we are doing is almost the same. Okay, so we approximated this term, this nonlinear term, by a linear functional. So because this is a functional, this is given by expectation of some function g bar with respect to the distribution Q. Okay, so the determination of g bar is given by the nested dual averaging technique that is given by like this. So here g bar t is a time average of the gradient. So weighted average of GS. So S is a time step. So S equal 1 to T. So at time T, so we take this expectation of GS, average of GS from S equal 1 to time T. And so each time T, this term, the gradient is calculated like this. So this is a kind of a functional gradient of this term with respect to the density function. So yeah, this term is the same as. So sorry, I go back. So this term is the same as this term. Okay, so we take the differentiation of f with respect to mu is given by like this. So this differentiation is coming. So coming here. Okay, so then after we linearize this term like this, so then objective function becomes this like this one. So the linear functional plus entropy term. So we have an explicit form of this Okay, so we have an explicit form of this optimization problem that is given by like this. This is a so-called Gibbs measure. Qt plus 1 is given by like this. So okay, so we have a Qt. So suppose that at time t we have a Qt. So then Qt is updated to Qt plus 1 by using Nesterov approximation, Nesterov dual averaging. This is the next step solution. Okay, then we substitute Qt plus 1 to here again, and then so we again compute the gradient and then we update. But the problem is that so to calculate this gradient, we need expectation. So we need to calculate the function value of the mini-field neural network. For that purpose, we run the gradient arrangement dynamics to sample a particle from this distribution. Then so you can use any MEC method anyway. So this expectation can be approximated by the finite particle average. This. Okay. Yeah. So then we repeat this algorithm many times. Yeah. This is a algorithm description. We calculate the gradient. And we take the average of the gradient. This is the dual averaging method. To calculate the gradient, we use a finite particle approximation of the neural network. So this corresponds to considering finite width networks. So basically, we are considering infinite width network, but we approximate it by the finite width network. The width M neural network is coming here. Okay, then. And so we update Q to Qt plus 1, and that has an explicit form like this. Now from this, we sample M particles. So each particle corresponds to the parameter of each neuron. Then by using these particles, so we calculate the finite sum like this. Then we iterate this. Okay, so then we have some convergence guarantee. Okay, in the outer loop, we have 1 over T convergence. And the second term corresponds to the number of parameters, so number of particles. That corresponds to the width of the network. If the width is large, then this term can be negligible. So you mean that if you consider very overparameterized network, then this term becomes small. So here appears some benefit of a overparameterized network. So if you consider very wide network, then so the optimization guarantee becomes better. Okay, so now if we neglect here, so then this term is 1 over T. So this is the polynomial order convergence. In the inner loop, so we need to sample the parameters that the time complexity of the sampling can be given by like a t square. So at time t, so t square computation is sufficient. So anyway, to obtain the epsilon accuracy, we need epsilon to minus third gradient arrangement, gradient update sufficient. So yeah, the important point here is that we have the polynomial order time complexity to obtain epsilon accuracy. So this is the first time, this is the first method that achieves this polynomial order convergence. And there have been other methods, like the people from Stanford, and they consider this kind of a method, so they consider mean field arrangement dynamics, but well, basically there appears an exponential order, so exponential. So to achieve the epsilon accuracy, so what they have considered required exponential to epsilon inverse. So there appears an exponential complexity, but this is a polynomial order complexity. Okay, so here are some numerical experiments that it converge. Okay, so I skip this one. So if you know stochastic dual coordinate ascent, so we can combine the stochastic dual coordinate ascent with this particle method, and we have an exponential convergence. Yeah, so in the particle dual averaging, we have a 1/t convergence in outer loop, but it can be well improved to exponential convergence if the objective function is a finite sum loss function. Like in an empirical risk minimization, so the objective function is just a finite sum of the loss. So then we have an exponential convergence like this. Yeah, but yeah, I skip this one. So yeah, finally, so this is also the final remark. So we have considered two methods of particle dual averaging and a particle stochastic dual coordinate ascent. Both methods can be extended to infinite dimensional particles. I mean, so we can extend the input x to infinite dimensional Hilbert space. Like maybe you want to consider functional data as an input. So then, even though the input x is extended to Hilbert space, so then we can construct a method that achieves that almost the same convergence rate with the finite dimensional settings. Like yeah, so if you extended x to the Hilbert space, then the first layer parameter is also extended to the Hilbert space. This inner product in a Euclid space is extended to inner product in a Hilbert space. So anyway, so we can construct almost the same algorithms. Yeah. Okay, so that's it. So thank you very much.
So thanks, Professor Suzuki. If you have any more questions, then you can ask.
Yeah.
You start with a fixed m, fixed t system. Right? There are two ways to go to this endpoint. One is you take t to infinity first.
Yeah.
That means you are looking at the 16 distribution for a finite time system, and then let m go down to infinity.
I see.
Not a fixed point.
Yeah.
But the other way is to come this way, which is you, for example, first take m to infinity in a finite time setting. That's the ODE, and then you look at sort of the fixed point of the ODE.
Right.
So in the proof techniques here,
Yeah.
So are you following this path or?
Okay, so so there are two ones. So in the first part, so like in the convergence. Okay, so here, I'm considering only the time t. So here, so the path is like this. We have m to infinity at a finite time. So then first we take m to infinity, then we take t to infinity. But to construct this implementable method, so we need to consider finite m, then we let t go to infinity. So therefore, in practice, so yeah, we can increase n as t goes to infinity. So we can increase both t and m simultaneously. But so basically, what we are considering is that so we set the precision epsilon beforehand, and then we take the sufficiently large m, then we run the algorithm. Yeah, that is our. Oh, okay. Sorry. So that is our the implementable algorithm. Yeah. Okay.
So in your convergence group, there was this one bound that was determined by the depth of the network. So
yeah,
why is it explicitly called like a two-layer convergence? So why not like up to 100 layers? So 100 layers is also like good.
You mean, so is it maybe so you mean, so can we extend this to the multi-layer neural network? So that is your question.
The problem.
Hmm?
But if if t is something greater than 2, like let's say 3 or 4, so why will this?
Okay.
Is the dimension of
That,
not the depth.
okay. Oh.
Yeah. So yeah. Okay. So yeah. Right. So we are not increasing the depth. We are just increasing the depth with this. And the problem is that there. Okay. Well. Okay. So I go back here. This formulation is very important. Okay. So we want to model the neural network F mu as an expectation like this. So this holds only for the neural network, a two-layer neural network. So unfortunately, so yeah. So because we have a two-layer neural network, the two-layer neural network is just a summation like this. So we can.
And the more we will have like chain of summations, right? Summation and then inside one more summation
yeah.
increase, right?
We can. Yeah.
So if
Theoretically,
like
we can.
nested integrals.
Yeah, but we needed to share the distribution. So
Yeah,
we have a nested, but in a lower layers, distribution should be shared by same with the all particles. So we need to consider some constraints. So, but theoretically, we can consider like that. So yeah, so it's not so easy to extend it to multi-layer. But somebody is trying to extend this mean field analysis to the multi-layer settings. So yeah, but basically the essence is like a two-layer neural network. So we have a two-layer network, and on top of that we have multi-layers. But those analysis ensures the deeper layer is a kind of isometry. So the input from the input from the two layers output is propagates properly to the output. So everything is reduced to the two-layer neural network. So that is the current limitation.
And in the experiments, you compared with what, SGD or?
Yes, we did. Well, yeah. So it depends on the situation. So sometimes the SGD is very, very good. And but sometimes mean field method, our particle method is good. So yeah, this is a SGD, and this is a mean field method, so our method. So
which data set, which problem?
Okay, so it's the true function is something like that. So we consider two binary classification. So there are inside and outside, very, very simple situation. So yeah, so if you require many neurons to separate two classes, then the mean field, so our method is likely to better than vanilla SGD. But if the target function is very simple, so like if you need this very small number of particles, so then SGD works well. But yeah, but I believe that the vanilla SGD also behaves something like mean field arrangement. So, yeah, we need to fill the gap between SGD and our technique.
But I think like one of the ideas in this would be, can we take the expectation of gradients to determine the Gaussian noise?
Gaussian noise.
Yeah. How much noise to take? Can we determine that within the expected gradient?
You mean you mean so okay? So this is this expectation is
like you are pushing it a little, right?
Yeah.
So can you estimate how much to push depending on the expectation of all the aggregated gradient that you have collected so far?
Okay, expectation with respect to the stochasticity of the history.
How much push it needs to have? So how much noise?
Well, yeah, it's difficult. So yeah, well, maybe how much noise, how large noise is required depends on the Hessian of the objective so surface. And well, so maybe in the local regions, so it could be very sharp. So in that case, the noise could be small, but maybe there is still some possibility that there is another large